3, 2, 1.
Hello, welcome to Innovating for the Earth, the story of Calix, an Australian company, their technology and the difference it's making. Today, we're discussing iron and steel, which is Australia's largest source of export income. So what is the scale of the climate challenge with steel making? Why is it considered to be such a hard to abate industry? What technology solutions are emerging? And what are their implications for Australia? From Calix, I'm joined by Chris Ormston, General Manager for Sustainable Processing. Chris leads the development and commercialisation of Calix's technology applications in iron and steel, alumina, and critical minerals like lithium. I'm also joined by two guests from the Superpower Institute, not an organisation you can only get into if you can see through walls or fly, but a not-for-profit dedicated to helping Australia seize the extraordinary economic opportunities of the post-carbon world. So Chris McMahen is the technical lead for green iron at the Superpower Institute, responsible for the evaluation of alternative green iron and steel making technologies and positioning the iron ore industry to continue supplying the raw materials required by a future decarbonised iron and steel making industry. And Max van Someren is the Managing Director of Bivios Australia, a techno-economics and sustainability consultancy that collaborated closely with the Superpower Institute in the preparation of their recently released report, A Green Iron Plan for Australia. So welcome all. Thank you very much for joining us. Let me start with you, Chris, from Calix. For those listeners new to the Calix story, a quick overview of what Calix does and where does the term Mars for Quitters come in?
Yeah, thanks, James. So, at Calix, we're an environmental technology company with a mission to solve urgent global challenges in industrial carbonisation and sustainability. We've essentially got a core platform technology that enables the processing of a wide range of minerals utilising an indirect heating platform that can be fully renewably powered and significantly reduces industrial emissions. So we're developing and demonstrating our technology in multiple markets: cement and lime, lithium, critical minerals, alumina, direct air capture, water, agriculture, and of course, iron and steel. So that's in a nutshell, Calix. Now, why is Mars for Quitters? Well, I believe this tagline was originally coined by one of our engineers during a team dinner a few years back, discussing a certain former advisor to the US government's vision to move humanity to Mars. Well, there's only one Earth, and we want to do everything we can to keep it spinning and to sustain human life here. So let's solve global challenges on Earth, because Mars is for quitters.
Very good. Chris McMahen, what is the Superpower Institute? What's your role there?
Good afternoon, James, and thanks again for the opportunity to join the discussion today with Max and Chris. Superpower Institute, or TSI for short, as you mentioned, it's a not-for-profit think tank. It was founded by possibly Australia's two most famous or renowned economists in Ross Garnaut and Rob Sims. The mission at TSI is to undertake the deep and fundamental research, which then informs public policy and market settings, specifically as it pertains to climate ambition, and in particular, seizing the superpower opportunity before us here in Australia. So myself, I joined TSI around 12 months ago as the technical lead for green iron, principally to support the recently completed green iron report that you mentioned. And now we're pivoting to other green metals and materials, as well as some WA-specific projects that we'll be looking at. Before joining TSI, I was employed in the resources sector for around about 30 years, most recently leading the green iron program at one of the major Australian iron ore producers.
Well, Max, tell us about Bivios and your collaboration with the Superpower Institute.
Yeah, sure. So the collaboration with the Superpower Institute
started 8 or 9 months ago on a task which was due to take 2 or 3 months, and it took 8 or 9 months before we finally published the report. So it really grew legs over time. But it's been a fantastic journey working closely with the Superpower Institute team. Bivios is a techno-economics company. So what we do is we use our technical understanding, and I'm an engineer by background, and our economics understanding. I have lots of finance colleagues, and I have economic training myself, to understand if a potential project and investment will actually stack up and make sense. If you think about this in your own life, if you were to install solar panels on your roof, for example, there'd be a form of techno-economics which would happen there in making that decision, because you'd look at the cost of the solar panels, how much energy you're going to save on your bill, and so on. I started talking to Bathan, the CEO of the Superpower Institute, about doing a similar thing, but not looking at the cost of solar on your rooftop, looking at the cost of producing steel or iron in different locations around Australia, off the back of some work that we had done looking at the modelling of a renewable energy industrial precinct in Western Australia at Oakajee. Bathan had heard about this work. He could see how we could repurpose the modelling work that we had done to come up with a step forwards in the level of detail in the public domain in terms of understanding the cost of producing iron in different locations and using different technologies around Australia.
So for all of you, really, your collective focus is on meeting global climate commitments, maximising the opportunities that decarbonisation may present. We're focusing today, of course, on iron and steel. Back to you, Chris McMahen, how big's the problem, going up in the helicopter and widening our focus? How big is the problem of carbon dioxide emissions in iron steel making?
Yeah. So I'll start with the numbers that are in the public domain. Every report references these, and that is that estimates of CO2 emissions related to steel production are between 7 and 9% of the global total CO2 emissions. So it is an enormous volume of emissions, and therefore it's an inescapable challenge. It can't be ignored. It is one of the principal industries under focus for decarbonisation. So with regards to the problem, I see it as a binary thing. It's sort of complex, but also simple. Let's start with the simple part. So the most widely utilised fuel for reducing iron ore and producing steel is coal. The next most favoured fuel is natural gas or methane. And I'll put aside for the moment recycling of scrap and electrical energy. So a substitute for carbon in the current use of fossil fuels is to use green hydrogen. It's a gas. It actually is part of hydrocarbons, so it is already playing a part in that process. But if we substitute coal, natural gas with green hydrogen, then we can effectively remove the CO2 emissions from the iron making and steel making. So that's the simple part of it. The technologies, such as the Zesty technology that Calix is developing, they are already there. There are already technologies that can use hydrogen. The complexity is in the economics. So the steel industry is very, very large, global steel industry. It's invested enormous amounts of capital in the infrastructure, and that infrastructure is fully embedded in the value chain. So the steel products generally get passed directly on to the next manufacturing step, whether that's industrial machinery or automotives. It's very well integrated. So there's a big incentive to continue to use those assets because they have a long economic life in front of them. So that's the first challenge in the economics, is the very high cost of capital to replace existing infrastructure and the capital intensity of new infrastructure. The second complexity in the economics is the cost of producing that steel. So using hydrogen, which is a developing industry, and particularly green hydrogen linked to renewable energy, is more costly than using coal. Now, both Ross and Rod, if they were given the opportunity to answer this question, would jump straight into it and say there's a market failure happening here in that the use of carbon is not penalised for the emissions in the existing technology. If that market failure was corrected, then the cost of producing green steel with things like green hydrogen would be competitive. So the reason I'm saying that is complex is it means ultimately the cost of producing steel in the future will increase because it is artificially low at the moment because of that market failure. And if you compare it to alternatives to steel, it's very, very cheap. Steel is very, very cheap. And even other industrial metals like copper and aluminium are orders of magnitude more expensive than steel. So it's not unreasonable to expect steel production costs in the future to increase as we pivot to a low carbon solution.
So Chris, at Calix, you've developed the Zesty technology. The problem it's trying to solve is what, and how does it work so that not only you can understand, but I can too?
So I'm now faced with the challenge of trying to describe the technology without a diagram, and our CEO famously uses a toilet roll in most of his presentations.
It's hard to do PowerPoint on podcasts.
So, Zesty is a renewably powered direct reduced iron technology for the production of green iron and ultimately green steel. It's an application of our platform technology that I mentioned earlier, which introduces hydrogen for the reduction of iron ore. And that's essentially removing the oxygen from iron oxide. So H2 goes in, it attracts the O off the iron oxide and exits the system as H2O. So it's a process that can be easily powered by renewables using no carbon-based fuel and therefore generating no carbon-based emission. It's a fines-based process, so it operates at low pressure as well, so with non-complex process control. The iron ore fines are introduced simply into the top of the process and fall or float through the system by gravity, and the hydrogen is introduced into the bottom and moves upwards, so it's what we call a counterflow. And the hydrogen simply strips the oxygen from the iron ore as it passes through the vessel, if you like. So the indirect heating enables hydrogen to be used solely for reduction of ore, no combustion, and therefore it's got the ability to achieve the minimum theoretical hydrogen consumption. You need 54 kilos per ton of hydrogen to reduce iron oxide. So every technology using hydrogen, given the costs of hydrogen, it's important that you can use the most minimum amount possible. And furthermore, as the heating is external to the process reaction, the system can also be turned down and ramped quickly. So this provides some operational flexibility, which is critical when working with future renewable energy grids. So that's the process, and the product that exits the process is a direct reduced iron product that's consumed in downstream steelmaking processes.
It seems, Chris, that there are many possible processing routes to make steel. Can you explain more about them and how they may be applied to different types of iron ore or decarbonisation pathways?
Yes, there are. There are many ways to process iron ore into steel, and the first step is processing iron ore into iron. And rather conveniently, there's no other way of making steel other than using iron ore or recycling existing steel through scrap and EAF. Our report looked only at hydrogen-based alternative reduction processes. There are many other alternative processes, some that use electricity directly, but they also require certain conditions in the technology, reagents and other processes. We focused on hydrogen only, as that is the most well understood and publicly accepted pathway of replacing the carbon portion of reduction in iron making with a similar alternative gas in green hydrogen. So that was the focus of our report, but we certainly have also privately evaluated many other nascent and emerging technologies.
Max, we've been ignoring you. My apologies. Your time to shine. As collaborator on the report with the Superpower Institute, what were some of the key findings from your perspective?
Well, I think the first and most obvious one is that this is really a story about energy as much as it's a story about iron. And when you look at the value chain for producing green iron, it's all about how you generate renewable energy and then use that to do the iron reduction process, which Chris has already described. If you think about the amount of energy we're talking about, it's really, really significant. So depending on the technology and the processing route, you could be talking about between 4 and 6 megawatt hours per ton of iron. A megawatt hour would keep the average Australian home going for about 2 months, so it's a lot of electricity. And each of the locations, we looked at producing 2.5 million tons of iron. So you multiply those things together and you just see, and it's an enormous amount of electricity, like significant proportions of the electricity grid, whether you're in Western Australia, where I am, or in one of the eastern states. And that energy has to be generated from a renewable source. Now, that creates all sorts of interesting downstream challenges, which we've already touched upon, because sometimes there's lots of renewable energy available in the middle of the day when the wind is blowing, and sometimes in the middle of winter when it's been very, very not windy for a week and very cloudy, you've got very little renewable energy. So you have all sorts of design decisions to make about the design of the system to try and deal with that intermittency, and you have different ways of tackling it. So you can put it in forms of storage for the electricity. You can try and store that electricity in a battery and then use it when you need it, but batteries coming down in price, but are still expensive. If you're converting that electricity, if you're using that electricity to generate hydrogen, which goes into the iron making process, you've also got hydrogen as something which you can store as well. But again, hydrogen storage has a cost associated with it. So the third way in which you can deal with that intermittency is you can actually tolerate some of that intermittency in the iron making plant itself. You can allow, when you run out of hydrogen in the middle of the winter and on that cloudy week, you can actually turn the iron plant down. And some technologies enable you to do that, and some less so. And that's one of the key things that we looked at in this report. What was really interesting was that there was a benefit from that flexibility, which knocked on through to the total cost of iron production per ton of iron. If you have the flexible operation of the plant, it means that you can do this trade-off between how often you run the plant and when and how much you overbuild the upstream storage of hydrogen, electricity, and so on. But the other benefit it gives you is it also enables you to start to play a more active role in the electricity market as well. So when electricity prices are really, really high, you can say, I'm not going to produce hydrogen right now, and I can turn off my plant if it runs out of hydrogen. That's no problem. Conversely, when prices are low, maybe you want to, overproduce. So that flexibility we found did offer potential benefits. We flagged that up in the report, and there are multiple different emerging technologies for iron production which enable that flexibility. So I think it was the flexibility which was the biggest surprise to me from the work that we've done.
So Chris McMahen, you mentioned Zesty earlier, and I think you said the technology is already here in reference to it. What have you seen from Zesty in its testing of Pilbara ores?
So I can't speak to the specifics of the results, but I can talk in a general sense to the nature of those results. So my team and I provided the Calix team with a range of ores out of Pilbara, from very, very high grade material to effectively waste, and then several other data points in between. And this is a very typical approach by iron ore producers and steel makers, is to throw your best and your worst material at technology developers and just see how it performs. The reduction of the iron ores was successful. So that was as expected. I think the thing that sort of stood out with Calix compared to some of the other organizations or companies we were dealing with was just the nature of the people in the company. The technical people were incredibly curious and really engaging. So it wasn't a case of sort of an arm's length relationship where we provided samples and they provided results and both parties stepped away. The two teams engaged really closely in a collaboration, and we had a lot to provide as iron ore producers in terms of our knowledge of the mineralogy of iron ores, how they perform in different processes. And of course, the Calix team were able to, inform us about the nature of the Zesty technology itself. So it was true collaboration effort, but also the management team at Calix are really interesting and great bunch of people to work with, very dynamic, very entrepreneurial, and very engaging. So the entire experience was really positive, and it's one of the reasons, although that was several years ago, it's one of the reasons I've sort of remained close to the team at Calix and very interested in their progress.
Well, you've said nice things about management in general. Now let's drill down into Chris Ormston, in particular, his strengths and weaknesses. No.
What I can do, though, James, is give you a bit more insight into the results of processing the ores. I think I'm free to do that. So we've tested a range of Australian ores from across all the different producing regions, so all the way across the country, of course, including the Pilbara. So it includes hematite, goethite and magnetite ores of varying grades. To date, we've done over 130 tests using 9 different Australian ores. And we've processed low grade down to 53% grade. And we've reached metallization in excess of 95%. So I think 98% was our peak metallization result. And we've proven with these tests that the Zesty system can be tuned to produce a consistent commercial grade of hydrogen direct reduced iron product. And furthermore, this reduced iron has also been formed into briquettes, which is the transportable form of DRI. And we've also undertaken provisional melting tests. And both of those activities have yielded highly encouraging results to date. So, we're on a mission to keep testing and keep developing.
Chris McMahen, Zesty was chosen as one of 2 technologies modelled in the Superpower Institute's Green Iron report. Why did you choose to model Zesty, and what attributes make it attractive to iron ore producers, steel makers, or both?
Well, James, first of all, it was hydrogen-based, as I mentioned before. So that was convenient. It was comparable to another less flexible or non-flexible technology that was also hydrogen-based. Some of the key attributes of Zesty, which helped in our decision-making, is scale was one of them. Scale's really important. We often associate scale or economies of scale with large, and that's very, very typical in the mining industry and in the iron and steelmaking industry. However, economies at a small scale are also very important, and particularly this will be the case in green iron. So many of the iron ore resources in Australia that are really well matched to making green iron and co-located with renewable energy are at a smaller scale. And the owners of those resources are also have lower capital capability. So having technology that works at small scale as well as large scale can unlock the economics of some of those stranded resources, whether it's geographically stranded or economically stranded. Now, I can't speak in detail to the cost of producing the components of the technology. Chris Ormston can talk to that. But my assumption is the nature of the technology means the majority of that production can be done off-site, which then lowers the capital cost of installing equipment or building equipment in remote locations. So maybe Chris Ormston can come back to that later. The second point is the efficient use of hydrogen. The hydrogen is not consumed in generating energy, and it's not lost in the process if it's not immediately reducing the iron, meaning it can be recycled. The hydrogen that is unreacted can be efficiently collected and recycled. So it's very efficient, and given that green hydrogen is one of the biggest cost inputs to green iron making, that's very important. The use of electrical heating, and this is me reflecting on my experience in industry, it's far more controllable, more precisely controllable, and particularly the patented calciner technology that Calix has and deploys in Zesty. That is one of the key attributes of the technology. And lastly, the flexibility in operating, as in ramping up and down to match renewable energy. Max will talk to how important that was and how big a factor it was in the economic modelling, but it can't be understated. The cost of building out overcapacity in renewables for both generation of electricity and production of hydrogen, storage of the same, is a huge factor in the investment in green iron making. So those were the key reasons why we chose Zesty.
So, Chris Ormston, do you want to just fill out the rest of that point the other Chris was making about scale?
Yeah, the technology that we have, it's an indirect heating vessel, if you like. So it's the next stage that we hope to go to with this, we've already gone to with other applications of the platform technology. That takes us to a single unit of 30,000 tons per annum. And the individual unit doesn't get any bigger than that. It's a modular expansion. So a lot of future-facing technologies are not necessarily single huge vessels that have traditionally needed to be so large because of the way in which they operate, the lack of efficiency they have in consuming carbon fuels, and they need to be big to be efficient. Whereas our platform technology can scale modular wise, and therefore you could have a bank of 100,000 tons, 200,000, 500,000 tons, 1 million tons, to best suit the supply chain that you're providing. So you could have large scale facilities at the mine site or at the port prior to shipping a green iron product, or you could also have the facilities at the steel mill that receives the direct shipped ore, and the processing can be done there. In a steel mill, maybe a 300,000 ton complex as opposed to a 4 million ton complex. So there's certainly a lot of flexibility in how large these facilities can be. And I think it promotes the opportunity to look at mini mills rather than mega mills, and also balancing the size of plants with the renewable power that's available in the region.
Chris McMahen, that all sounds great. On the flip side, what concerns do you have for Zesty or indeed other leading direct reduced iron technologies to scale? What are the barriers?
My concerns really are again around the economics, not really the technical aspects of it. I think the science is really well understood, and the technical capabilities of the Calix team and the Zesty process are sound. Key concerns are around technology scale up and the sort of first of a kind investment risks. It's really quite difficult for investors to take that kind of risk in this environment. They need to have those additional investment risks identified. And, a big part of the recommendations coming out of the Superpower's Green Iron Report are policy mechanisms and market mechanisms to help address those risks. So again, technology, I'm very comfortable and confident about that. The economics are the challenges.
So Max, turning iron ore into green iron sounds like it would need a lot of renewable energy and green hydrogen, which might then need even more renewable energy. How does that all fit in with Australia's energy needs and ambitions and plans and everything else?
Australia has an incredible opportunity in the 21st century within the context of a decarbonising world. We often talk about Australia as a lucky country. We're lucky once again because we're in a place which has got immense renewable energy resources, lots of wind, lots of sunshine, of course, space, and able to put your wind farms and your solar farms. But the trouble is we're also a long way from lots of other places. And so if we just try and export that renewable energy through a cable, well, we might be able to get that to Singapore. There's projects which are looking at doing that, but it's difficult to go much further. If you try and convert that renewable energy into an energy carrier, something like hydrogen, which can then be used as energy at the other end, that has its own challenges associated with it as well. I mean, hydrogen is very large volume, difficult to move around. So instead, a key thesis of the Superpower Institute, as laid out in an earlier report they did called the New Energy Trade, which is really good, is that we should be using as much of that renewable energy as possible to generate the products that the world will need in future, the low emission products that the world will need in future here. And iron is the largest single opportunity. There's other ones like sustainable aviation fuel, silica, polysilica, aluminium. But iron's an incredibly large market, and we also have the advantage of being a very large iron ore producer as well. So it's not so much that what we're talking about fits in with Australia's current domestic use of energy. It's more about how we're going to use that energy in the future, and iron's key role in it.
So if we couple energy-intensive industrial facilities with electricity grids, what might be the potential challenges and the potential benefits? My bill's going to go up or down, light's going to stay on or go out.
So there should be, there is a lot to work through here, and this will keep people who work in the techno-economic space like me busy for many years to come. But there is enormous potential for benefit once you're able to operate an industrial plant more flexibly, because it helps to balance out the grid. And that intermittent supply of renewables, which I talked about, is of course not just supplying industrial facilities, but it's supplying our homes and businesses as well. And we want stability in the prices that we pay for our power. If we've got large industrial processes which can turn off or turn on to match what's going on in our own lives, then that should eventually drive down the costs of electricity.
I think that's what I wanted to hear. Chris Ormston, is grid integration something Calix has considered much? Do you see an opportunity there?
Certainly the technology is compatible with intermittent and renewable sources of energy. There's the potential for technologies like ours and others to support further renewable energy integration into the grid, lowering grid balancing costs, enabling more economical industrial energy uses, as Max has mentioned. Already in our pilot facilities, we've simulated the swift ramp down and turn up of power as soon as ramping down as soon as the products exited the system, and then swift ramp up to operating temperatures before reintroducing the feed. So this is a great example of having an ability to avoid high energy costs during peak loading periods on grids. It takes me back to the very beginning of my career. I studied in Sheffield and started in the steel plant there. We had an electric arc furnace. It's still running today. And in the winter, you'd drive into the plant and the yellow lights would be flashing for load management, which meant we had to switch the electric arc furnace off at 4:30 so that the city of Sheffield could all go home and switch the kettles on. And so you had to manage your tap to tap times so that the furnace was off power, and then got to 6:30, everyone's had their tea, switch the furnace back on. So that, this isn't new in industry, and there's been ways.
Well, it's not new at homes. Whenever I'm having a shower, I have to shout down the stairs, "Can you stop doing the washing up? I need some hot water up here." Yeah. So there's that sort of load management, perhaps.
That's right.
Most people can relate to in some way.
Yeah. So broadly speaking, across our platform technology, the flexibility to ramp production up or down, depending on electricity price and availability, helps enable the lowest cost of production. And this is, of course, extremely important for green iron making. But furthermore, Calix is also developing hybrid heating solutions that can rapidly switch between electricity and a second heat source without interrupting production. So these are the things we also need to think about. And we see this as more important for other applications of the technology that will be retrofitted to existing continuous production industrial facilities like cement plants or alumina refineries. By enabling hybrid heating, industrial heating could switch to lowest cost source of energy available based on daily and seasonal volatility in the energy markets. Hybrid heating could also further help balance electricity grids by increasing or decreasing electricity use as the grid needs, again, without a decrease in industrial production. So there's lots of things for us to think about.
And within all that, where do you see Zesty fitting in, and where do you see it being most successfully deployed?
My personal view is the investors that will be most highly incentivized to both take up those kind of government and policy supports and to deploy technology like Zesty are those that are not currently participants in the industry. So they'll be investors with either a stranded iron ore resource or a renewable energy resource. I mean, economically stranded, but they just don't have the capital to get up into the existing market. So they'll be highly incentivized to develop a project and participate in the market. The technology, Zesty technology, will unlock some of those opportunities. I think South Australian, particularly magnetites in South Australia, there's some really prospective projects there. And in Western Australia, around the Midwest Coast region, which was identified in Max's modelling, that's one of the really prospective renewable energy locations, but it's also got abundant iron ore, which has struggled to get up to market in the current iron ore market conditions of low cost and large scale. So that's locally. The second place I see this being really well picked up and deployed is in emerging or growing economies in Southeast Asia, where there's a demand for green steel, there's a small renewable energy potential, and the iron ore is either local or it can be imported. And that's where the economies at smaller scale and deployment become really important for Zesty. They can support very small scale green steel in those emerging economies. So for me, there's probably many others, but for me, those are the two that stand out.
And are there, again with you, Chris, any applications that you think might be more challenging for it?
Yes. By comparison, I think that the biggest challenge we face is our current iron ore industry and the majors that are participating in that industry. The economics are incredibly attractive in just producing and selling iron ore. There's a real disincentive to invest in downstream processing. Currently, there is no major iron ore producer in the world that is also a steel producer. There are some steel producers who look to diversify and invest in iron ore. But if you've got an iron ore asset, you're making really good margins, so you're not incentivized to produce green steel. So that's a challenge not just for Zesty, but it's a challenge for all of the new alternative iron making, is the people who really should be investing in this space are the ones with the least incentive to do so.
Chris Ormston, you've been sitting there very quietly and peacefully while he's been talking about your technology. It's almost like someone talking about one of your kids. What comments do you have about Chris McMahen's assessment?
Well, certainly regarding deployment of the technology, there's a huge opportunity here for Zesty to play a part in securing a green iron export future for Australia, first and foremost, which is hundreds of millions of tonnes per year. The technology's got the flexibility and application to be located, as we've discussed, at mine sites, at ports, at steel mills. And this, of course, depends on the CapEx and OpEx considerations when taking a decision on any project. It all needs to stack up technically and economically. No doubt the cost and availability of renewable energy is key for green iron making. Technologies and flexible operations are critically important for future-facing technologies such as Zesty. Zesty technology can substitute the need for pelletizing iron ore fines, and there's examples of things being done quite differently in different parts of the world. So there's no pelletizing plants in the Pilbara. The fine ores are shipped and pelletized close to the steel mill because it's more economic. Whereas in Brazil, all the pelletizing plants are lined on the ports, and the fines are, and that's a lot to do with the grade of the ore and the price of producing pellets in Brazil, and there's an export pellet market rather than a DSO export market. So there's things done differently today, and where Zesty or other technologies that are more novel reside, then I guess the market will decide whether they're at the mine or at the steel plant. So there's but the options are there for all. Regarding future successes and challenges, I mean, for Calix, we continue to develop our technology, advancing through the technology readiness levels, and our proposed demonstration plant provides us with the next scale-up opportunity to further validate the technical and commercial readiness and performance, and mitigate and solve those technical risks that exist with all new technology deployments. If we don't develop and test, we don't know, and if we don't fail somewhere along the line, we don't learn. And the industry needs to accept that new technologies don't always, nothing goes swimmingly. There's always setbacks. There's always things but if we don't try, we don't learn. And I think in Calix, we've got an extremely honest approach when it comes to our technology development progress, and we're not afraid to share our results as we go, and also accept the feedback.
Yeah. So, Chris Ormston, where would you hope, in a realistic way, Zesty was in 5 or 10 years?
Well, our immediate next step, as I just mentioned, is to have everything in place to enable us to build our 30,000-ton demonstration plant here in Australia. This is a 5-year project. It includes building the facility, commissioning and ramp up, and a significant period of operational performance testing. The outcomes from the demo plant will directly inform further engineering work that's required for a commercial scale facility. These facilities may be required to produce in excess of 1 million tons to 2 million tons, depending on where they're located in the supply chain, as we've discussed during the podcast. So that takes us to 2030. And in the meantime, we'll continue to utilize our existing testing facilities in Victoria, working with our industry partners, both domestically and internationally, to keep testing ores and advance our technology roadmap. That enables us to provide a market competitive green iron product, or a technology that will deliver that. A technology that provides flexibility of operations conducive with renewable grids. And we aspire to be the process and product of choice for future steelmaking routes by providing a breakthrough technology that's pioneered and demonstrated in Australia prior to international adoption. So in 10 years' time, I guess our vision is to be, to have commercial scale facilities that are built and operational in a number of locations, and that those locations are on Earth and not on Mars.
Beautiful. Squared the circle right at the end. So last question, final comment from each of you. The potential of the iron and steel industry is very large, but what do you think really needs, assume some decision makers are listening, what do you think is practical things that are needed to be done soon to maximise the opportunity?
So, James, the TSI report identified 9 key recommendations which can be summarised into these key areas of policy support, which will enable the development of the green iron and steel industry in Australia. So the first one was the federal government's current hydrogen production tax credit of around $2 per kilogram of green hydrogen. That is helpful. And at around 55 kilograms of hydrogen per tonne of green iron, it works out to around $110 of support per tonne of green iron. However, the modelling that Max and the team conducted at TSI indicated that the level of support needs to be around 170 Australian dollars per tonne of green iron. So that's the recommendation out of the report. And coincidentally, that's around about the social cost of 2 tonnes of CO2 emissions per tonne of current grey or black steel production. So that was the first one. Second recommendation was either the government invests directly or supports private investment in common user infrastructure. So these assets are very capital intensive. So transmission lines, ports, roads, energy storage, pipelines for transporting hydrogen and so on. Some of these projects will be too small to support that capital investment for their own standalone projects. So we need government support for common user infrastructure. Third recommendation was developing a green hydrogen certificate scheme, because in the early stages of this transition, it may be more cost effective to produce hydrogen in a location that is not where you want to produce the green iron. So the green iron industry may be able to pay for the cost of that hydrogen, but not have it proximate to you. So if you can develop a certificate scheme that allows that to be traded between locations, that would be incredibly helpful in getting the industry started. Capital support for green iron projects greater than 500,000 tonnes per annum capacity. This is a really key one. I want to make sure this is clearly understood. It's detailed in the report. This can be funded from the government's existing federal green iron scheme. So they've already allocated funding for this kind of support. And TSI recommends that it comes in 2 different tranches. And this is quite important for companies like Calix and technology like Zesty. The first tranche of 15% of capital support, project capital support, would be for any green iron technology project, so irrespective of the technology deployed. But the second tranche of a further 15% capital support would be targeted at first-of-a-kind technologies like Zesty. So that acknowledges the risk associated with developing new technology and the benefit that fast followers receive that the initial investor doesn't. So 2 elements of capital support capped at $500 million per project. So that's the key capital support. The final 4 recommendations were around government policy. So first one was matching the EU's CBAM, or Carbon Border Adjustment Mechanism, with a local guarantee of origin and standing up a like-for-like policy in Australia. Increased support for R&D, not only in technology, but also in developing markets, in price discovery and incentivising international trade in these type of green commodities. Third one is engaging those trade partners to support and participate in all of the above. So working with our natural trade partners, particularly in Asia, like Japan, Korea, Taiwan, and China. And the last one was to advocate for consistent international carbon pricing, particularly our obligation to set a new or a next stage emissions target in the Paris agreements. So government putting in place those policy settings and the support for the industry investors is critical to developing the industry.
And for those listening, there will be a test on those 9 recommendations at the end of the podcast. How many can you get, Max?
I think that our modelling shows that producing green iron in a way which can be competitive is within arm's reach, but it still requires support at this stage to get to the point where it is actually a cost competitive way of producing iron in the absence of a carbon price, which is a whole nother discussion. I do think there's enormous potential from technologies which either use hydrogen or they use a direct electrolysis route, which enable you to operate more flexibly. And there is still much work to be done there to mature those technologies. Calix is doing fantastic work on the Zesty process. Others are working as well. I think we need to continue that innovation support, stay the course, so that when those technologies do get to the right level of maturity, that happens in Australia, and Australian companies and projects can take advantage of them.
Chris McMahen?
I believe we're right on the cusp of this. I think the technology is there, and there are other technologies following fast after, as Max has just mentioned. The real missing piece is the policy support mechanisms that allow investors to put their capital at risk. That is really the key. The other pieces of the puzzle, as far as I'm concerned, they're already there. There's already a community expectation. The industry is ripe for transitioning and looking for capital support to deploy the solutions. There's a growing market demand for a green iron product, and we have the abundant natural resources, both renewable energy and iron ore. And even more critically, within Australia, we have the innovators like the people at Calix to deliver the technology solutions. So what we really need is that support mechanism from government to get the investments going.
And finally, last words, Chris Ormston.
Yeah, certainly similar to Max and Chris's comments. As a technology company, we have to stay the course to keep developing this technology to help realize the transformation that's required to truly decarbonize heavy industry. It's certainly a challenging and complex journey, launching novel technologies into heavy traditional industries. And as with everything, it takes a village to achieve success. And I recognize the importance of the relationships we hold with our partners in industry and government in achieving our goals. Our industry partners need to continue supporting these innovations as the ultimate beneficiaries of adopting technology that secures a sustainable future for the processing of minerals and metals. And government policy and associated agency funding mechanisms have developed positively in recent years, but in practice, applications consume a significant amount of time and resources to complete. It's years, not months. So I think we do need to find a way to move a lot faster.
Yeah. Look, thank you so much for your time. It's been really, really interesting, Chris, and Max. Thanks. And we will talk to you next time on Innovating for the Earth.